Today I'd like to talk to you about short intervals of time, intervals shorter than a second, and some of the ways that we can measure them. Now, there are a number of ways of getting into this subject, but today I'd like to take one specific event, something that we're all fairly familiar with, and something that we think of as happening fairly quickly, and see how accurately we can time it. The event that I'd like to study is lightning. The average lightning flash lasts for about a half a second, and it appears to the eye to flicker a little bit. If you were very fast, you could probably measure the total duration of the flash with a stopwatch. But let me ask you this. Does the flash start from the cloud and go down to the ground, or does it start from the ground and go up to the cloud? And that flickering, what's causing that? Is it because one single stroke is varying in brightness, or because there are a number of strokes, one coming right after the other? You probably don't know the answer to these questions, because the eye just doesn't respond to many things that happen very quickly. But in physics, very often we have to know what happens in very short intervals of time, intervals as short as a millionth of a second. So we have to develop special techniques for studying them. The first technique I'd like to talk about today is a photographic technique. About 100 years ago, photographers were making still pictures of lightning by time exposure. Most of the pictures, as you would expect, came out looking like this, but then a picture was taken by this same method, which came out looking something like this. At first, some thought a strong wind had blown the lightning sideways. Then they began to experiment a little, and they found that pictures like these always resulted when the camera was knocked sideways when the lightning struck. In order to understand what this picture of lightning shows, we must first realize the significance of the fact that the film was moving sideways while the picture was being taken. To make this clear, let's do an experiment. When I push this switch, the battery causes the pin in this recorder to move and mark this piece of paper. I'll start it. The mark shows that I have closed the switch, but it doesn't show for how long. And if I close and open the switch more than once, I cannot determine the number of times that I've done it from this record. But by doing one simple thing, by making the paper move, I can put much more information on the record. The length of the mark is now a measure of the time I closed the switch, and it is immediately obvious how many times I've done this. In order to measure these intervals, I'll have to know what speed the paper is moving at. This timer is quite accurate. I'll hook it up to the same switch so that it starts and stops along with the pen. That was 2.5 centimeters on the recorder and 5 seconds on the timer. So when the paper runs at this speed, 2.5 centimeters, about an inch, equals 5 seconds. Now, I trust this timer for a number of reasons. Every time I do the experiment, the recorder and the timer agree. And the recorder agrees with my watch, and it agrees with my own sense of how long 5 seconds is. But if I want to measure events that happen much more rapidly, I can no longer judge from my own sense of time whether the recorder and the timer are right. All I can do is speed up the recorder by a known amount. When the paper moves 25 times faster, 1 centimeter should correspond to 0.08 of a second. This mark is a little less than a centimeter, indicating a period of about 0.07 of a second. This is also how long the timer indicates the switch was closed. So we see this technique works in measuring shorter intervals. If I move a piece of film rather than a paper, I should be able to perform the same kind of experiment, except this time I will mark with a light source rather than with a pen. This experiment will take us right back to our pictures of lightning. Here are my light sources. A fluorescent light connected up to the 60-cycle power lines, and a candle. I'll light it. If we take a still picture of these two, we get something like this, very much as the eye sees it. Now I'll take a picture with the camera moving. The camera is mounted on this phonograph turntable. With all this weight on it, the table will turn at a little less than 30 revolutions a minute. The circumference of the table is 60 inches, so when the motor is running, the film and the camera will turn in this direction at a speed of 1 inch in a 30th of a second. I'll press the shutter when the camera is pointing in this direction. The picture will be taken and the shutter will close when the camera is over here. The candle, which was on the bottom, left a smooth, steady smear across the picture. The fluorescent bulb, on the other hand, has made a series of spaced lines. Now, if I measure these lines, I can tell that in a 30th of a second, the time it takes the film to move a little less than an inch, the light goes on 4 separate times. In 1 full second, then, the bulb would be blinking 120 times. Now here's that picture of lightning again. This is no longer an enlargement, but is the size of the original negative. In the camera that took this picture, the film was moved in this direction at a speed of about 2 inches per second. If a stroke of lightning were a single flash, this stroke would make a solid blur across the film the way the candle did. But this picture looks much more like the one of the fluorescent bulb. In this flash, it looks like there were 22 separate strokes. If we measure, for example, the distance between the 4th and the 5th stroke, we find that it's a 1/16 of an inch. The film moves 2 inches a second, so we know these strokes occurred 1/32 of a second apart. In a sense, this sort of picture is a graph in which time is plotted as a distance. But for all we know, each one of these strokes may consist of many more strokes. The most obvious way to look for more detail is to move the film faster. Now, there are many types of cameras which do this. One of them is in operation at the New Mexico Institute of Mining and Technology at Socorro, New Mexico. This camera moves the film past the lens at a speed of 12 inches per second. The film, which is about 8 inches wide, is held on 2 spools in this carriage, which can be revolved at a constant speed. The film comes off one spool, is held flat behind this plate, and goes onto the other spool. After each exposure, the film can be advanced behind the lens by turning the spools. If you held a pencil against the film at the point where the lens is, it would draw a circle on the film as it turned. For the same reason, exposures taken through the lens come out as circular pictures. The camera in its housing is mounted in this shelter on top of the research building. The installation can be maneuvered to cover any part of the horizon. The camera on the right is the so-called slow-speed camera, which tracks back and forth at 2 inches per second. The faster-moving camera is simultaneously taking pictures of the same lightning strokes. This photograph is an enlargement of a picture taken in New Mexico with the slow-moving camera. This is a picture of the same stroke of lightning taken with a faster-moving camera. The circular piece of film has been cut into 5 sections. Now let's look at stroke 24. On this slow-moving film, it appears as a single flash. Where the film is moving 10 times as fast, it now appears as 2 separate parts. The film moves in this direction, so we know that the faint stroke on your right came first, coming from the cloud down to the ground, followed by the brighter return stroke, which goes from the ground up to the cloud. By knowing the speed that the film was moving, and by measuring the photograph, we can show that the faint stroke started down from the cloud 1/1000th of a second before the brighter return stroke got back up to the cloud. As we continue to measure shorter and shorter times, it becomes more and more difficult to refer to times the way that we have. 9 10,000ths of a second, for example. So let's do this. Let's call 1/1000th of a second a millisecond, 1/1000th of a second a microsecond, and 1/1000th of a millionth of a second a millimicrosecond. Now, in our photographic techniques, measured events that occur in this time range. Now let's study things that happen 1,000 times faster. To do this, we're going to use the oscilloscope, a very common research tool. This tube is similar in many ways to the one in your television set, and it's similar to the one in the oscilloscope as well. Back here, a beam of electrons starts out and strikes the face of the tube. Where it hits, it causes the chemical to glow so that we can follow the motion of the beam. If I connect the positive lead of the battery to this terminal, the beam moves over to your right. If I connect the positive lead over on the left-hand side, the beam moves to the left. On top, moves up, and on the bottom, moves down. I can do the same thing with my oscilloscope. Up, down, left, right. We're going to use the oscilloscope to measure short time intervals. In our camera experiment, we moved the film and we kept the light source still. In the oscilloscope, we have to do it the other way around. We keep the film, this screen, still, and we move the light source, the beam of electrons. I need to make the spot move at a known uniform speed across the tube face. This movement is called the sweep because the spot sweeps uniformly across the screen. I can vary the sweep from once every 50 seconds all the way to once every 10 microseconds. At faster sweeps, it looks just like a line. Now I'll set the sweep for 1 second and do the same sort of experiment we did with the pen recorder. Instead of a switch, I will use a flashlight shining on this photocell. When I block the light to the photocell, I do the same sort of thing as opening and closing a switch. This causes the oscilloscope beam to move up and down. The length of the deflection is a measure of the length of time my hand was in front of the photocell. If I move my hand in front of this twice very quickly, we can see immediately that 2 separate events occurred. Now, to show you how the oscilloscope can measure very rapid events, I will try interrupting the light thousands of times faster. I'm going to use this motor and gear. The gear has 140 teeth and turns at 60 revolutions a second. I'll position the photocell so that the light passing through the small hole falls on it. When the wheel turns, the teeth momentarily block off the light, as you can see on the scope. Now I'll start the motor and adjust the sweep speed so that the beam crosses the grid once every millisecond. Now I'll count the number of interruptions. From here to here is 1, 2, 3, 4, 5, 6, 7, 8, and about a fifth. That's 8.2 interruptions in a millisecond, or 8,200 per second. Now, this motor runs at 60 revolutions a second, and there are 140 teeth on the gear. So this means that the light is being interrupted 8,400 times a second. When we made the experiment on the oscilloscope, we got 8,200 interruptions. So the scope is measuring correctly to about 2%. If I use a higher sweep speed, I can measure down to microseconds with this scope. The oscilloscope is used to examine fine details of lightning strokes when used with this sensitive photocell unit. This cell responds to minute, very rapid changes in the intensity of the light in lightning strokes. The photocell is here mounted at the top of this observation tower at the New Mexico Institute. It is connected to an oscilloscope in a room within the tower. You see two lines on the scope face. One records the changes in the output of the photocell. The other records electrical changes in the atmosphere. This viewer makes it possible for an observer to watch the oscilloscope, while at the same time, a 35mm camera makes a constant photographic record of the patterns on the tube face. Photographic records of the oscilloscope patterns are cataloged and studied in detail. Each of these lines is a photograph of one sweep across the oscilloscope face. These lines can be drawn end to end and scaled up in size for more careful study. In this chart, we see strokes 4 and 5 of one lightning flash. They were separated by 41 milliseconds. If we look closely at stroke 5, we see that it lasted from here to here, 2.4 milliseconds. You can see clearly where the return stroke started. If we look at stroke 4, we immediately see how it differed from stroke 5. Here, the leader stroke lasted longer and was not as brilliant. The return stroke was more abrupt also. The total stroke lasted 4.5 milliseconds. In this oscilloscope record, we can see details of the various parts of the lightning stroke. Details in light fluctuations only 10 microseconds in duration. Lightning is an exceedingly complicated electrical discharge. We have by no means shown all the techniques used to measure it. But the purpose of this film wasn't to give you the last word on lightning. What we wanted to do was to look at something that happened too rapidly for us to be aware of directly, and show you some of the techniques and equipment used to measure it. Equipment such as a pen recorder, a high-speed camera, and an oscilloscope. There are other techniques for measuring short time intervals and observing events of short duration. For example, this simple stroboscope. With this sort of tool, you can take a long, careful look at recurring events like the turning of a fan blade. And there are exceedingly high-speed motion pictures, which, when projected, slow down action for analysis. There is one thing that all these techniques share in common. They all extend our awareness of the world around us past the limitation of our senses.